Alright, so today we're going to move into section 8.4. We're going to talk about plane curves and parametric equations. Alright, so in problem 1 here, you see an example of a parametric equation. So a parametric equation is written in kind of a strange form. Your x is given as a formula. X is 6t minus 4. And y is also given as a formula. Y equals 3t. And this is called parametric. We tend to think of t as being a time parameter. So at different times, we'll get different x values and different y values. So to graph these sort of things, it asks us to sketch the curve using arrows to indicate direction. We're going to pick some of our favorite numbers in the whole wide world and plug them in for t. 0, that's always a good number. 1, -2, -1, -2, and 3. All right, so those are our favorite numbers, I guess, to plug in. Half sounds like a fraction. All right, we only use half this time. All right, so I plug 0 in. And it's kind of a pain in the neck because I've got to plug it in for both of them, don't I? All right, so I plug 0 in, I get -4. And I plug 0 in here, I get 0. All right, so I'm going to start plotting my points here. I'll put a quick scaling on my graph. Each little dot is one spot. So -4, 0, 1, 2, 3, 4 is right there. All right, now plug in 1. When I plug in 1, I get 2. And here when I plug in 1, I get 3. So then I've got the point 2, 3. You'll see how much you like that when we get to the next group of problems. All right, plug in 2. 8 and 6. 2, 3, 4, 5, 6, 7, 8. And then 6 up. 1, 2, 3, 4, 5, 6. Looks like it's right about there. All right, then let's jump down to 3 since we were doing the positive numbers. What happens when I plug in 3? 14 and 9, so that's way out here somewhere. Like so. All right, now plug in -1. -10 and -3. So -10, let's see, do I have enough dots here? 4, 5, 6, 7, 8, 9, 10, I do. And -3. 1, 2, 3. Right about there. And finally plug in -2. -16. So look, it looks like this dot kind of looks out of line here, but that is just approximating this dot. You're right, it looks like it makes a line. However, when we draw a parametric equation, we also have a direction. So for example, when I first plugged in 0, I got this -4, 0 right here. When I plugged in 1, I went this way. When I plugged in 2, I went that way. So not only is it a line, but we also indicate direction. Which direction? Well, we put little arrows to indicate that when time gets bigger, you're moving in that direction. When time went from 0 to 1 to 2, we moved from left to right.
So we did go back to 3,
Well, I really should have gone 0, 1. I really should have gone -2, -1, 0, 1, 2, 3.
Yeah.
So I put my points in order.
So it depends on how we did it.
Well, yeah. But, I mean, we put our numbers in order, and then it always works out. We didn't put our numbers in order in the box, which is kind of what confused things. Well, time can sometimes go backward. Well, for example, if I'm dealing with an application problem, and my data starts in the year 2000, I can talk about what happened in the year 1999, which would be t would be -1. So sometimes t can be negative. Sometimes time can be negative. Sometimes it can't be. We'll see. In the next example, for example, time can't be negative. All right, anyway, so we've done number one. We sketched the curve. The curve happened to be a line, and we used arrows to indicate direction. The direction went that way. Then it says, determine a rectangular coordinate equation. So that means write it in the way we always write it, like y equals something. Well, this is a line, so we ought to be able to write the equation of that line. How do we do that? I could find the slope. That seems kind of hard, actually. The slope is half. 3/6. Here's a better way to do it. I'm going to take this equation right here, and I'm going to get the t all by itself. What do I get when I get t all by itself? How would I get t all by itself? So t equals y divided by 3. And then I'm going to take that, and I'm going to plug it into that equation. So x equals 6 times y divided by 3 minus 4. In other words, x equals 2y minus 4. So, is that the equation of a line? No, why not? What do you mean y is oscillated? Oh, isolated.
You want to get y by itself.
So if I get y by itself, would it then be a line? So how come it's not a line right now? It is a line. It's just not written the way we normally write a line. So to make people happy, let's get the y all by itself. So x plus 4 equals 2y, and then divide by 2. So 1/2 x plus 2 equals y. So it is a line. And there's the equation of that line. All right, well, let's do the next one, and the arrows will make more sense, I think. All right. This time, I'm going to pick some of my favorite numbers in the whole wide world for t. What kind of numbers would I pick? How about 0? 1. I don't like 2 very much. I don't like 3 very much. I like 4. I like 9. I don't like 5. I like 16. So what kind of numbers are you picking? I'm looking that one of my things has a square root in it. So I want to pick numbers that are going to make square roots to be easy. So I think I want to use 0, 1, 4, 9, 16, and 25. And I think we're going to see really have an issue when we do that, but we'll deal with it. Let's start with the x's first, because the x's are easy. What's the square root of 0? What's the square root of 1? Square root of 4? 3, 4, 5. Yeah, I can pick clever numbers there. Now let's figure out the y's. What's 0 to the 4th? 0, and 0 plus 1 is 1. You're giving me the final answer, that's right. What do you get when you plug in 1? 1 plus 1 is 2. What do you get when you plug in 4? What do you get? 17? Bigger than 17. Because I'm plugging in t, not x. So I actually have 4 to the 4th.
56.
How much? 256 plus 1, which is 257. What happens when you plug in 9?
65,500.
Say it again.
65,500.
You have to add 1.
Come on, 9 to them.
You do 9 to the 4th,
Yeah.
and then you have to add 1.
9 to the 4th is, oh, I did it 6. Yeah, 6,500.
So final answer should be 6,600.
6,562.
6,562. 62. All right,
Next
well,
one is, I skipped one.
all right, well, let's plot what we have so far. We have 0, 1, which is right there. We have 1, 2, which is right there. We have 2, 257. 257's way, way up there somewhere. Just based on those 3 points, what is this looking like? It's looking like a parabola, but it looks like that parabola is going up super fast, doesn't it? I would agree. So it looks like this. What's that? Why would it come back down? In this case, it doesn't. We're missing half the parabola. We should have another half over here. But to get the other half over here, we would need to use negative t numbers, but we can't use negative t numbers. We would get imaginary answers, correct. All right, now, so what's the direction? Well, this was my first point. This was my, no imaginary half parabolas. No. So my direction this time, again, would be like so. Because I started here, as my t got bigger, I went this way. Well, what does it look like? Looks like half a parabola, doesn't it? Yeah.
Small. Instantaneous.
So parametric equations are very commonly used for things that are in motion. So the x value depends on time, the y value depends on time. You plot those things and you get the motion of the object. All right, so now can we write this in rectangular coordinate form? Very irritatingly, okay. How irritatingly?
Well, you subtract 1, y minus 1.
That would be one correct way, but I think there's a better way. Wouldn't it be easier to get the t all by itself in this one this time? Yeah, I think so. So sometimes you want to get the t all by itself here, sometimes you want to get the t all by itself there. You pick the easy one. So t, using the easy one, x is the square root of t. So x squared equals t. And now I take that and plug it into that equation. I have y equals x squared to the 4th plus 1. What's x squared to the 4th? X to the 8th, not x to the 6th? You don't add them there? Don't let me talk you out of the right answer. X to the 8th plus 1. So this really isn't a parabola. It looks like a parabola, but parabolas comes from things that have x squared. This has x to the 8th. So it's not a parabola, but it kind of looks like one. It should, but because of this parameterization, we're only getting half of it. Because we cannot use negative t numbers.
So would it be wrong to say that 0 squared 0 x is
You're absolutely correct. When we're writing this in rectangular form, we do have to say you can only get half of the shape. So we really should say you have to limit your domain. X can only be greater than or equal to 0 to only get half of the whatever it's called. Sort of like a parabola thing. I don't know that it has a name. All right, now let's do some fun ones. Funner. Oh, crap. What the teacher did this time. Put trig things in there. X equals 2 cosine t. Y equals 3 sine t. And I'm telling you, I only want you to use t values between 0 and 2 pi. 0 would be a great one. You like pi over 4? Pi over 2. 3 pi over 4. Pi. 5 pi over 4. How about, we'll do 2 more. 3 pi over 2 and then 2 pi. So we'll make a bigger table here. All right, so let's do the x's first. We'll plug in 0. What's cosine of 0? And 1 times 2? 2. Pi over 4. What's cosine of pi over 4? Root 2 over 2, and then you multiply by 2. So you get square root of 2. Okay. Pi over 2. Cosine of pi over 2? 0. That's correct. So there's a 0. 3 pi over 4. 3 pi over 4, I'm over in quadrant 2. So cosine is negative. And then I'm going to multiply by 2. I'm going to get that same answer again. Negative square root of 2. Pi. Cosine of pi. Negative 1, but then again I got to multiply it by that 2, so I get negative 2. 5 pi over 4. Still going to be negative square root of 2 because it's just down in quadrant 3, but it's all the same stuff, isn't it? So negative square root of 2 again. 3 pi over 2. No. Cosine of 3 pi over 2 is 0. That's correct. Because we'd be straight down. If I had written 7 pi over 4, sneak that one in, that one would be in quadrant 4, and cosine is positive in quadrant 4, so that would give us a square root of 2. And then back to 2 pi. 2 pi is the same as 0, isn't it? So that's going to give me a 2. Alright, so there's all my x numbers. Now let's try the y numbers. Now I'm using sine. What's sine of 0? 0. What's sine of pi over 4? But then I got to multiply by 2, I get.
Multiplying by 3.
Oh, crap. I'm multiplying by 3 this time. 3 square root of 2 over, that's x. How do I take a nice number like 3 and multiply it by a fraction, square root of 2 over 2?
3 square root of 2.
I think of 3 as being 3 over 1, right? I don't multiply the bottom. So it's going to be 3 square root of 2 over 2. Alright. Sine of 0. Sine of 0 is 1. Cosine of 0 is 0. And then 1 times 3 is 3. Alright, now what's going to happen here? 3 pi over 4 is in quadrant number 2, but it's really the same as pi over 4, isn't it? So I'm going to get, and sine is positive in quadrant 2, so I'm going to get the same answer again. I'm going to get 3 square roots of 2 over 2. How about a pi? What's sine of pi? Sine of pi is 0, so that's going to be a 0. 5 pi over 4, now I'm getting into quadrant 3. What happens in quadrant 3? It's negative, so I'm going to get negative 3 square root of 2 over 2. 3 pi over 2? Nope. Cosine of 3 pi over 2 was 0. Negative 1 times that 3 gives me negative 3, yeah. 7 pi over 4, that's in quadrant 4. So I'm going to get the negative answer again. Negative 3 square root of 2 over 2. And finally, 2 pi is the same as 0, I get 0. Alright, so I have points that look like this. I have, let's do the easy ones first. I have 2, 0. I have 0, 3. I have negative 2, 0. And I have 0, negative 3. Yeah, because look, because it's going to be very symmetric, isn't it? I'm going to have square root of 2, 3 square root of 2 over 2. That's going to be, square root of 2 is over here somewhere, and that's going to be there somewhere. Then in quadrant 3 and quadrant 2, I'm going to have that point. In quadrant 3, I'm going to have that point. In quadrant 4, I'm going to have that point. So you're exactly right. It makes an oval, or the fancy math word for oval is an ellipse. This makes an ellipse. Okay. Which way do I draw my arrows? What direction did it go? When I plugged in 0, I got this.
Sorry, counterclockwise.
This is going counterclockwise, isn't it? Because this is when I plugged in 0. This is when I plugged in pi over 2, pi, 3 pi over 2. So it's going that direction. So my arrows indicate that we're moving in a counterclockwise direction. When those kind of clocks go extinct, we'll use Google spins this way when it's thinking, and the other way. So it'll be Google and anti-Google. Counter Google. So it'll be Google and counter Google. I've already thought of that and figured it out. All right, now here comes the fun part. Here comes the fun part.
It's like do the way of higher.
How do I write this in rectangular form? I can't? So? This one wasn't a line, yet I could write it in rectangular form. It's not a line, it's a curve.
And that's an infinite curve.
This is an infinite ellipse. It goes round and round. Oh, here's what you do.
Yes, it does.
I'm going to take this and I'm going to divide both sides by 2. So x over 2 is cosine t. I'm going to take my other equation, y equals 3 sine t, and I'm going to divide it by 3. So y over 3 equals sine t. Then I'm going to use my all-time favorite trig identity. What's your all-time favorite trig identity? No. No. That's your all-time favorite trig identity. Sine squared t plus cosine squared t equals 1. But instead of sine squared, what happens when I square this thing? What's sine squared? So y squared over 9 plus cosine squared would be x squared over 4 equals 1. So there's the equation of that ellipse written in standard rectangular form. How are you supposed to remember these things? Well, I just showed you. Other than that. All right, the last one. You can go home and graph that one, but I'm going to show you how to put this one into rectangular form also. We have x equals cosine t, y equals cosine 2t. It kind of reminds me of back when we were... Yeah. So it kind of reminds me of back when we were doing identities. When we had one that had a t and one that had a 2t, we used one of our special formulas, which was the double angle formula. So the double angle formula for cosine, there were 3 of them. I'm going to use this one. This is 2 cosine squared t minus 1. So now I can take this, x equals cosine t, and I can plug it in right there. I have y equals 2x squared plus 1. Because I have cosine squared, but cosine is x, so cosine squared is x squared. So when you go home and you draw this graph, what kind of picture are you going to get? You should get a parabola.